So now we need to begin the topic of sequences and series, which we'll deal with pretty much for the remainder of the semester. We first talk about sequences, and that leads us into the concept of series. We won't deal with sequences for a whole lot of time, but we need that in order to get to the concept of a series. So, an infinite sequence. An infinite sequence, or sometimes we just call it a sequence, can be thought of as a list of terms written in a definite order. That's a really vague definition of what an infinite sequence is, but it kind of gives you an idea there. A list of terms written in a definite order. Mathematically, it's best for us to think about a sequence as defined as a function whose domain is the set of positive integers. Positive integers starting at 1, then 2, 3, 4, 5, 6, etc. So we denote a sequence by a couple of ways. One, we can think about a function and using something similar to function notation. We could just list the terms of the sequence themselves, in which case we could use the subscript notation, so a sub 1, a sub 2, a sub 3, a sub n, etc. A sub n would just be considered the nth term of the sequence, some random term, and if it's an infinite sequence, it would keep going beyond that point, because an infinite sequence will go on forever. So more specifically, we could probably write in here an infinite list of terms. Infinite list of terms written in a definite order. All right. We're not really going to talk so much about a finite sequence, so every time we say sequence, we're going to refer to it as an infinite sequence. So if we think about sort of more of the function concept, where the domain is the set of positive integers, we could sort of look at it in this function format, where we have a formula that will generate the terms of the sequence. So in this case, a sub n is defined as the sequence 3 plus negative 1 to the n. So we could look at what a sub 1 would equal, in which case a sub 1 would be when I plug 1 in, so 3 plus negative 1 to the first would give me 2. A sub 2 would be what happens when I plug 2 into the sequence for n, and that would give me 3 plus negative 1 to the second, so that would be 4. Then a sub 3 would be what happens when I plug in 3, etc. You get the idea. I would get 2, a sub 4 would be 4, a sub 5 would be 2, and I could just keep going there. I could figure out, the beauty of using sort of this notation is I could figure out what a sub 100 is just by plugging 100 into this formula, and I could get any term of the sequence that I want. And a sub 100 would be 3 plus negative 1 to the 100th, which would give me 4. Okay, so obviously there's terms in between here and here, but that's the idea. Okay, here's another one, b sub n. And in b sub n, we could figure out what b sub 1 is. So b sub 1 would be what happens when I plug 1 in. So 1 over 1 minus 2. So that would be 1 over negative 1. B sub 2 would be 2 over 1 minus 4. So that would be 2 over negative 3. B sub 3 would be 3 over 1 minus, what's it going to be, 6. So 3 over 5. B sub 4 would be 4 over 1 minus 8, so 4 over 7, etc. And so what we can do here is we say, okay, well, here are the terms. That's all well and good. Here are the terms of this sequence, and it's just a couple of the terms. But the big question we're going to ask, well, two questions, and this is something we're going to have to build up to, but we're going to get to it fairly quickly, is does it appear that the terms of any of these sequences, and these are only two of them, but does it appear that the terms of this sequence are approaching some finite value? And if so, what is that finite value? So sometimes it's pretty clear, like this sequence right here, I think it's pretty clear. You're just getting 2, then 4, then 2, then 4, then 2, then 4, over and over and over again. So it's not really approaching a single finite value. In this case here, what do we have? We have negative 1, negative 2/3. This should have been negative 3/5, negative 4/7. These should all be negative. Does it appear that the terms of this sequence are approaching a single finite value? And it doesn't quite look too obvious as much on this one, but something we're going to have to ask. And so we're going to get to that. Well, that's exactly the question you ask when you do the limit of a function. Does it appear that the y value of the function is approaching a single finite value? And so you know limits are going to play a role here. Also, we can also define a sequence recursively. Rather than just give the formula for the function and I could find any term of the sequence, we could define a sequence by looking at its previous term or terms. That's what a recursively defined sequence would do. So here's C sub n. C sub n is defined where it's the first term, C sub 1 is 25, and then this tells me how I'm going to always get the next term. C sub n plus 1 will equal C sub n minus 5. C sub n comes right before C sub n plus 1. So this says I'm going to take the term previous and subtract 5. So if my first term of my sequence is 25, the next term is based off of the previous term minus 5, so that would be 20, and then the next one would be 15, and then the next one would be 10, and then 5, then 0, then negative 5, etc. Okay? And there's the sequence. And again, does it appear that the sequence is approaching some single finite value? Okay? It's not always the question we need to ask about sequences. Sequences could be used for a lot of different things. For us to talk about it in terms of series, which is eventually where we'll get, that's the big question we're going to ask. A pretty famous recurring sequence, that's recursively defined, is the Fibonacci sequence. It doesn't really play a huge role for us right now, but it's a very, famous recurring sequence where f sub n is the sequence and the first term is 1, the second term is 1, and then every other term is defined by f sub n minus 1 plus f sub n minus 2. So it takes the two previous terms and adds them together. So in this case, you need to know two terms to find the next term, which is why we needed the first and second term. So the first term is 1, the second term is 1, the next term is those two added together, which is 2. The next term is these two added together, which is 3. The next term is these two added together, which is 5, and then 8, etc. So you see we get this sequence 1, 2, 3, 5, 8, 13, 21. It just keeps going. It's a pretty important sequence in nature. It first came up when they were studying the breeding habits of rabbits and how they multiply. You also see it in spirals, when you look at the spiral and kind of the seashell of how this expands. So it's a pretty important sequence when it comes to nature. We're not really going to study it so much right now, but it's just an example of a recursively defined sequence. So one thing we're going to have to do is, at first, just recognizing basic patterns of sequences. So sequences aren't always defined by their formula. Their formula tends to be the easiest way to work with a sequence, but it's not always the way a sequence is originally presented. And so this sequence right here should have dot, dot, dot on the end of it because it's an infinite sequence. So here it says find the formula for this sequence where a sub n is given to you in these first 5 terms. And then find a formula essentially that generates every term. That means when I plug 1 in, I get this first term. When I plug 2 in, I get this next term. When I plug 3 in, I get this next term, etc. Okay? So what's that formula going to be? Well, when it comes to the fractional ones, the best thing to do is to think about this sequence as a formula for the numerator separate from the denominator. Well, you clearly see a pattern in the numerator, 2, 4, 8, 16, 32. All right, and what you're seeing there is multiples of, powers of 2, in which case 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth. So 2 to the n would be my numerator. Now the denominator are consecutive odd numbers. So you can always write an odd number as an even number plus 1. So an even number plus 1 would look like that. An even number is a multiple of 2. You could also do an odd number as an even number minus 1. Okay? That'll always get you to an odd number. The question is which one of these would give us 1, 3, 5, 7, 9. We want to start with 1, especially when we plug 1 in. Well, if we plug 1 into this formula here, okay, we're actually going to start with 3. Whereas if I plug 1 into this formula, we'll start with 1. So 2n minus 1, that will generate our formula, and that will generate this sequence. So if I plugged 1 in, I would get 2 over 1. If I plugged 2 in, I would get 4 over 3. I plugged 3 in, I get 8 over 5, etc. So that is the formula that will generate this sequence, which will be the most beneficial thing we need when we ask the question, does it appear that the terms of the sequence are approaching a single finite value? All right, here's another one. This is another random sequence, okay? And we want to look at whether there's a formula for this. Well, they become hard fairly quickly. I mean, pattern recognition is something you've done since elementary school, right? You've looked at patterns of numbers. That's how you first start learning about working with numbers, is understanding their patterns. Obviously, by the time you get to this level, the patterns can get very complicated. The first one was pretty easy. This one's a little bit more hard, a little bit harder. Look at this. We have a negative, then a positive term, then a negative term, then a positive term. Whenever you have that, we call that alternating sequence, where the switches sign every other term. It would be created by using -1 to some power. We could either use the nth power, that would be if we're starting with a negative number, or n plus 1, and that would be if we're starting with a positive number. Notice we're starting with a negative, so -1 to the n, and that means when I plug 1 in, I get a -1. If I plug 2 in, I get a positive 1, etc. Now look at the numerator and denominators separately. So if we look at this numerator, 2, 8, 26, 80, 242. Not sure if you recognize a pattern there. Look at the denominator, 1, 2, 6, 24, 120. The denominator pattern might be more obvious to you in that I multiply by 2 to get this number, I multiply by 3 to get the next number, I multiply by 4 to get the next number, I multiply by 5 to get the next number. So I'm multiplying consecutive integers together. 1 times 2 times 3 times 4 times 5 times 6, continually stacking it up as I go. Well, that's exactly the definition of a factorial. So n factorial, if you haven't dealt with n factorial before, is when you multiply consecutive integers together. So 1 times 2 times 3 times 4, all the way up to whatever n is. So if you think about 1 factorial, that would just be 1. 2 factorial, that would be 2. 3 factorial, what? Because it's 1 times 2. 3 factorial would be 1 times 2 times 3, so that would be 6. 4 factorial would be 1 times 2 times 3 times 4, which would be 24. That's exactly the numbers you see here. So this is 5 factorial. A special definition for factorials is 0 factorial. 0 factorial is also 1. We need that special definition so that we can work with properties of factorials, so they make sense in some of the operations we do with them. But that's just a special definition because it doesn't make sense in the standard definition where we multiply consecutive integers, positive integers together. So anyway, this would be n factorial down here. And so then we look at this pattern in the numerator one more time. Well, let's say I give you this pattern, 3, 9, 27, 81, 243. If I gave you that pattern, I think you might recognize it a little bit quicker. Well, those are powers of 3. 3 to the first, 3 to the second, 3 to the third, 3 to the fourth. And how do they relate to these? Well, all of these numbers over here are 1 less than that. So let's say 3 to the n and minus 1. And so that formula, which should take some time to generate and figure out, but eventually you come up with, that's the formula that would give you the sequence. So it's all about pattern recognition, but the formula is a pretty important part to this because that's something we're going to use a lot. So next thing I want to start talking about is the limit of a sequence. So one way we can sort of think about the limit of sequences is picturing it. And we can picture it by plotting terms of the sequence on a number line, and that can help give us an idea about the limit of a sequence. Or we can even plot it on a graph, similar to like we would graph a function. Because remember, think about this sequence as a function whose Domain is the positive integers. So let's look at this sequence right here. N over n plus 1. So if I plug 1 in, I get 1/2, 2 in, I get 2/3, then 3/4, then 4/5, etc. And what we could do is we could plot each one of those terms on a number line. So if I plug 1/2 in here, and then I plot 2/3 on the number line, then 3/4 on the number line, then 5/4 on the number line, and I keep plotting these on the number line, it can give me an idea of what's happening with the terms of the sequence and where the terms of the sequence seem to be going. Well, basically what you see here is that the terms seem to be getting closer and closer and closer to 0. To 1. And that's in fact what's happening here. Now, this in no way is a proof that the sequence is approaching 1, but this is a good way to get an understanding of what's happening with the terms of the sequence and to get an idea of what the sequence could be approaching. So plotting it on a number line is one way to do that, but sometimes it will require you to actually plot a lot of terms to get an idea of what's happening. This case probably not so much, but in other examples, yeah. Is this foolproof? No. It's a lot like when you use the graph of a function to estimate what the limit would be. The graph of the function in no way proves that the limit exists or what the limit actually equals, but it gives you a good understanding of what the function is approaching. Again, we could use the function notation, kind of thinking of it as a function whose domain is the positive integers, and the graph consists of all these discrete points, 1, comma, a sub 1, 2, comma, a sub 2, so the domain is 1, 2, 3, etc., the positive integers, and the range is all the terms of the sequence, the things you get when you plug those integers into the sequence. So a1, a2, a3, so you look at these points. I start plotting these points where this axis is your terms axis, and this axis here is your positive integers. So think of this almost like domain and range. Okay? And we plot the points. So if we plug 1 into the sequence, we get a sub 1, which is here. And so we get this point. If we plug 2 into the sequence, we get a sub 2, which is here. Plug 3 into the sequence, we get a sub 3, which is here. And you start following the terms of the sequence with these discrete points, and you see that the terms of the sequence appear to be getting closer and closer to this horizontal line, which is 1. Okay? So again, giving you an idea of what's happening. But again, this is no way a proof of necessarily what the sequence is approaching or that the sequence is approaching 1, but it does give you an understanding of how the terms of the sequence are developing. So what we really want to do is come up with a more concrete way of finding the limit of a sequence. So one way to do that is with the formal definition of the limit of a sequence. So we let L be a real number. The limit of the sequence a sub n is L, and we would write that as the limit as n goes to infinity of a sub n equals L, if for every epsilon greater than 0, there exists a capital M greater than 0, such that the absolute value of a sub n minus L is less than epsilon whenever n is greater than m. This may sound somewhat familiar to you with the delta epsilon definition for limits of functions. And it is exactly that. I mean, it's the same concept that we had for the limit of the function, that in order for the sequence to approach L, the distance between the nth term and the limiting value has to get smaller as as n gets bigger. Okay, as n gets bigger and bigger and bigger, the distance between the nth term and the limiting value has to get smaller. That's exactly what this is saying. Okay. If this limit of the sequence actually exists, which it might not because limits don't always exist, we say the sequence converges and it converges to L. That's pretty important. Sometimes I hear people say something converges at a get value. That's not what we're going to talk about here. That will come up later in the semester where we talk about something converging at a value. But no, right now we're talking about the sequence converging to L. And if this limit of the sequence doesn't exist, which could happen, Then the sequence diverges. Okay. Remember, L has to be a finite real number. Okay. L has to be a finite real number, a single finite real number, in order for the sequence to converge, in order for the limit to exist. Now, the delta epsilon definition that we have here, as with the delta epsilon definition in Calc 1 for limits of functions, is not the easiest to use. It is the formal definition, but not necessarily the one we're going to use most often, in which case the one we'll use most often is essentially applying the function limit concepts we've learned so far and doing that. And that's what this is going to say. So the limit, let L be a real number, let F be a function of a real variable. So we have a function and we have a sequence. So let's say that we know how to do the limit of the function. And this right here should be an x. So we know how to find the limit as x goes to infinity of f of x equals L. That's the limit of a real valued function, in which case this is the type of limit you've been doing since the beginning of Calc 1. So let's say we know how to do that. We know the answer is L. Now let's say we have a sequence a sub n. A sequence is not really particularly the same as a function. We think of it as a function. But let's say we have the sequence a sub n, such that f of n equals a sub n for every positive integer n, which means when I plug 1 into the sequence and I plug 1 into the function, I get the same thing. They're equal. When I plug 2 into the sequence and I plug 2 into the function, they're the same. 3, 3, 4, 4, etc. Okay? Then that tells me if the function approached L, and since the function value and the sequence value are the same for every n value, then the sequence should also approach L. This is what we're going to use most often, because we can use all the skills we learned in finding the limits of functions to help us find the limit of sequences. And you think about it, we could use L'Hopital's rule, we could use a lot of the stuff we did with simplifying functions and then limiting them, like factoring, rationalizing denominators. We use things we know about vertical and horizontal asymptotes of functions. So we can use all the skills we learned for functions and apply that to sequences. So in this case, here we go. Find the limit of sequence whose nth term is given by this formula. Okay? So this is the way we compute the nth term. So we can find the first term, second term, third term, etc. So find the limit of that sequence. So we want to find the limit as n goes to infinity of a sub n. Now, if we could find a function that would generate all the same terms as a sequence does, and we could find the limit of that function, we could definitely do this. Well, it's real easy here. If we have the formula for the sequence, that is the function. So if we look at this function, so look at this function here, and we look at the limit as x goes to infinity of this function. If we could figure out what this limit equals, whether it exists and what it equals, then we could figure out what the limit of the sequence is. Well, this is a limit that we have done before. This is a limit you should have seen before. And we did this limit using L'Hopital's rule, and we found out that this was the limit that equaled E. If you don't remember, you have to go back to our L'Hopital's rule lesson, and you could review that, but this is the limit that equals E. Well, so if this limit equals E, and f of x, or sorry, let's say f of n equals a sub n for all positive integers n, that's the symbol for integers, then the limit as n goes to infinity of a sub n also has to equal E. And that's it. So using our function skills to find limits of sequences is going to be a pretty important thing. couple of properties here, very similar to the function properties, is if we have two limits that exist, a sub n equals L, b sub n equals k. Let's say we want to do the limit of the sum of the two sequences. Well, then we just do the sum of the limits. Same thing, we go for difference. If we have a constant multiple times one of the sequences, we just take the constant multiple times the limit. If we have the product of the two sequences, then we do the product of the limits, and the quotient of the two sequences, we would do the quotient of the two limits. Barring that, none of the terms of b sub n equals 0, and also the limiting value doesn't equal 0. Because we can't have any term be 0, that would mean one of these terms of this division sequence would be undefined. And we can't have the limiting value be 0 because then the answer would be undefined. And so if we look at, say, let's find the limit of this sequence here, if it exists. This is the one that we looked at in the very beginning, in which case we want to do the limit as n goes to infinity of a sub n and figure out what that is. Well, let's look at f of x equals 3 plus negative 1 to the x. Okay, what do we know? We know that f of n equals a sub n for all positive integers n. Okay, we also know that the limit as x goes to infinity of 3 plus negative 1 to the x doesn't exist. Why do we know that? Because we know that this thing just keeps switching back and forth between 2 and 4 and 2 and 4 and 2 and 4. So we know for a limit to exist, it has to approach a single finite value, and therefore it doesn't exist. So then we could say, therefore, the limit as n goes to infinity of a sub n also does not exist. Okay? We could also say that the sequence diverges. Okay? So therefore, this sequence diverges. All right? When the limit doesn't exist, the sequence diverges. This is one of the other examples we started off with in this lesson. And so if we want to do the limit as n goes to infinity, oh, my screen is not working out. The limit as n goes to infinity of b sub n, we'll figure out what that equals. What we're going to do is we're going to look at, say, f of x equals x over 1 minus 2x. We know that f of n equals a sub n for all positive integers n. Clearly, why? Because this formula and this formula are the same. We can look at the limit as x goes to infinity of x over 1 minus 2x. Hopefully you look at this and realize that the answer is negative 1/2. Why do you know the negative 1/2 is the answer? Because this is a simple rational function where the degree of the numerator and the degree of the denominator are exactly the same. When you have the degrees the same, what do? You divide the leading coefficients, which is 1 and negative 2. Give me negative 1/2. Or, option 2 is we could use L'Hopital's rule. X is going to infinity, so this numerator is going to go to infinity. The denominator is going to go to negative infinity. So we could say that this is an infinity over negative infinity situation, which would tell me that I should take the derivative of the numerator, which would be 1. I should take the derivative of the denominator, which would be negative 2. And now I'm doing the limit as x goes to negative infinity of this constant, which should just be that constant, and therefore I get negative 1/2 as well. So then we could say, therefore, the limit as n goes to infinity of b sub n converges to negative 1/2. Done. Okay? So your skills in limiting functions will come in a big way in understanding how a sequence's limit exists or doesn't exist. So here's another one, worded a little differently, but basically the same thing. Show that the sequence whose nth term is defined with this formula converges. Again, having the formula that function formula where if I know A1, A2, A3, A4, just by plugging in 1, 2, 3, 4, makes this so easy. So if I look at, okay, I want to find the limit as n goes to infinity of a sub n and figure out what that equals. Well, let's look at the function. F of x equals n squared, or x squared, that's a function of x, so the variable should be x squared over 2 to the x minus 1. What do we know? We know that f of n equals a sub n for all positive integers n, okay? Clearly, because these formulas are exactly the same, they're definitely going to equal each other. Can we do the limit as x goes to infinity of x squared over 2 to the x minus 1? Well, yeah, we should be able to handle this. As x goes to infinity, we know the numerator is going to go to infinity. 2 to the x also goes to infinity, so this is an infinity over infinity limit. So what we could do here is apply L'Hopital's rule, in which case we would take the derivative of the numerator. So we have the limit as x goes to infinity of 2x over the derivative of the denominator. So 2 to the x, if we do the derivative of that, that's an exponential. So it would be natural log of 2 times 2 to the x. It's not a natural exponential, it's a regular exponential, so that's why we need this ln of 2 here. In which case, as x goes to infinity, this numerator is going to go to infinity, this is going to go to infinity, so we got another infinity over infinity limit. So what we're going to do is we're going to take L'Hopital's rule again, in which case we'll get 2 over the derivative of the denominator is going to be ln of 2 times another ln of 2, so squared times 2 to the x. And looking at this now, as x goes to infinity, the numerator is just 2. It's going to stay 2. The denominator is still going to go to infinity, though. So you have 2 over the denominator goes to infinity. We know that if the denominator gets big, numerator stays constant. This whole thing is going to go to 0. So the limit of the function equals 0. So therefore, the limit as n goes to infinity of a sub n equals 0. So we can say the series a sub n converges to 0. All right, and using our function skills, we were able to get this done. Now, there were some more complicated methods of evaluating limits of functions you learned throughout the process of Calc 1, and one of them was the squeeze theorem for functions. So we could also apply the squeeze theorem for sequences in the same way. If we look at 3 sequences, a sub n, b sub n, and c sub n, and let's say we know the limit as n goes to infinity of a sub n, and we know the limit of as n goes to infinity of b sub n, and they both equal L. Okay. We also know that the sequence's terms line up in a way such that a sub n is always less than c sub n, which is always less than b sub n. So that means c sub n is stuck in the middle. It's squeezed in between a sub n and b sub n. Well, if the limit of a sub n equals L and b sub n equals L, but c sub n is always stuck in between, then therefore the limit as n goes to infinity of c sub n also has to equal L. This works out the same way as the squeeze theorem, or we can sometimes call it the sandwich theorem, in Calc 1 would have worked out. So here's an example. Let's look at, say, negative 1 to the n over n factorial. So something like this is our sequence. If we're trying to figure out what the limit of this sequence is, well, if we look at n greater than or equal to 4, okay, so at some point, and from that point on, in this case 4 on, that sequence is actually could be squeezed between a couple of different sequences, but here's 2, negative 1 to the 2 over n, 2 to the n, and 1 to the 2 to the n. Okay, we know that these two sequences are both going to converge to 0, and if this sequence is stuck in between those two, right, and we could show that by proving the inequality. We don't need to necessarily go through that here. Just the concept of the squeeze theorem is important. You can see that in this graph, that this, where are we here? Let's this right here, this curving sequence of terms, okay, is the sequence we're looking to evaluate. However, if we look at 2 to the n, its terms constantly go down to 0. Negative 2 to the n go to 0, but from the negative side. And since this one is stuck in between, not at first, but eventually it gets stuck in between, that's why we have to start at 4. Okay, this is where 4 would be right here. Starting from that point on, all the terms are stuck in between, then therefore this sequence also has to converge to 0. Okay? And that's generally how your squeeze theorem works. We don't use the squeeze theorem a lot in this initial stage of working with sequences because it's not very easy to use. The key is, the question would say, find the limit of the sequence. You have to randomly come up with these other two sequences that are both less than and greater than yours, and whose limits you know, and they equal each other, so that this whole thing works out. It's not an ideal situation when you're first dealing with sequences to apply. But just to talk about it is not that difficult. To understand how it works is not that difficult. So it is something that you should have some awareness about. Another tool we can put in our toolbox would be this absolute value theorem. This works really nicely when we have terms of a sequence that aren't necessarily all the same sign. They could be alternating, or they could just be, a couple of negative terms, a couple of positive terms. So what it says is this. For a sequence a sub n, okay, if the limit as n goes to infinity of the absolute value of a sub n equals 0, then the limit as n goes to infinity of a sub n also has to equal 0. So what this does is, by doing the absolute value of the sequence, it eliminates any sign of the terms. So no negative, no positive, everything just becomes positive. In which case then we can look at that sequence in a simpler form necessarily. And if it happens to equal 0, then the sequence itself without the absolute value should also equal 0. And the reason is kind of similar to that last example. If you have a sequence who has a negative term, and then a positive term, and then a negative term, and then a positive term, and a negative term, and then a positive term, etc., right? Looking at that. And if I make all those terms positive, so this comes up here, this comes up here, this comes up here, and all those terms are positive, okay? And it still goes to 0, then basically what that's telling me is that then this had to happen, that this term, even if it was negative, and this term, even though it was negative, and this term, it was negative, the terms themselves are still all going to go to 0 if, when I make them all positive, they go to 0. Because all that was happening was that since the terms were sort of switching sign back and forth and back and forth, they were still going to 0 just from opposite sides of 0 itself. And so that makes this a little bit easier when it comes to sort of the function concept, because lots of times when you include this, say like negative 1 to the n, it might be harder to do the limit with a function. But if we can eliminate that, so if I look at the limit as n goes to infinity of the absolute value of c sub n, that would be just the limit as n goes to infinity of the sequence without that alternating piece. So that would just be 1 over n factorial. What I can see is that if I use f of x equals 1 over x factorial, that would be equal to this for all positive integers. And if I did the limit as x goes to infinity of 1 over x factorial, I know the denominator goes to infinity, numerator stays 1, so that clearly equals 0. That's much easier than if I include the negative 1 to the n, which makes it a little bit more difficult to do this limit. But since this equals 0, then this equals 0, and then therefore the limit as n goes to infinity of negative 1 to the n times 1 over n factorial also has to equal 0. Okay. At some point, some of these little tricks that we learn along the way, and some of the tools in our toolbox from functions, they stop being efficient, and they don't give us the answer as nicely as we would like. So we have to look at maybe some other ways of doing it. And one other way that we can look at sequences and whether or not a sequence converges or diverges is based off of defining it as monotonic and possibly bounded. Okay, so we need to look at what the definition of monotonic and bounded is. And then once we do that, we can talk about how that relates to convergence. So, definition of monotonic. Monotonic is similar to increasing and decreasing, but a little bit more specific. So, first, a sequence A sub n is monotonic if all its terms are non-decreasing or non-increasing. So the idea of increasing or decreasing means that terms are getting bigger or terms are getting smaller. The monotonic is a little less than that in that the terms can also be staying the same. So a sub 1 is less than or equal to a sub 2, which is less than or equal to a sub 3, which is less than or equal to a sub 4. If it was just increasing, these would all be less than signs. And the other way around, it could be the opposite too. So monotonic covers both, whether the terms are getting bigger or staying the same, or the terms are getting smaller or staying the same. And so if we want to sort of determine whether or not a particular sequence like this is monotonic, we could do that by looking at whether or not these terms, inequalities, are holding. So one thing you should know is kind of have an idea going out. Are we looking for them to be getting bigger or staying the same or smaller? Sometimes that helps by looking at the first couple of terms. This one we already know is 2, 4, 2, 4, etc., which we clearly know that this is not monotonic. And so we can show this really easily that neither of these things is happening, and we can go from there. So to show this is pretty easy. Show something's not monotonic. You say, well, a sub 1 equals 2, a sub 2 equals 4, a sub 3 equals 2. So a sub 1 is less than or equal to a sub 2, but that's greater than or equal to a sub 3. So therefore, it's not monotonic. So you could simply just show that with a couple of terms that this doesn't work out to be non-increasing or non-decreasing. To show something is monotonic might be a little bit harder, so you have to show that this always holds. So here's another one. If we want to show whether or not this is monotonic, first thing I like to do is always look at a couple of terms so I get an idea. So if I plug 1 in, I get 2 over 2. If I plug 2 in, I get 4 over 3. Oops. If I plug 3 in, I get 6 over 4, etc. So get an idea of, does it seem like the terms are getting bigger or smaller? Staying the same, obviously, is something that we can do, but or none of that. So it looks like the terms are getting bigger. This is 1 and then 4/3 and then 6/4. So it looks like they're getting bigger, so I need to show that that's happening. How can I show that? I have to show that my computer is going to work. But first, I need to show that b sub n is less than or equal to b sub n plus 1 for all n, right? For n being positive integers, right? So this tells me that one term is less than or equal to the next term, right? So that it's this kind of increasing or staying the same. Well, what's b sub n? b sub n would be 2n over 1 plus n. What would b sub n plus 1 be? Well, it would be n plus 1 plugged in for n, so 2 times n plus 1 over 1 plus n plus 1. So I have to show that this inequality holds. Well, how could I do that? Well, I could cross multiply across this so that I can get rid of the fractions. So I'll have 2n times n plus 2 is less than or equal to 2 times n times 2 plus 2 times n plus 1. Okay, and I just distribute this 2 in. All right. What I can do here is multiply this, and I can say, okay, well, this is 4n 2n squared. Hold on here. That this is 2n squared plus 4n, and this would be 2n squared. Supposed to be 2n and 2n plus 4n plus 2. Well, seeing that this and this are the same, and this are the same, there's really nothing left over here. So 0 is less than or equal to 2. You know, if this and this are the same, this one has to be essentially plus 0 on it, and this has plus 2 on it. Clearly, 0 is less than or equal to 2 at all times. It's definitely less than. But it's less than or equal to 2 at all times. So therefore, this inequality holds, and B sub n is monotonic. Okay? So that's one way you can show that a sequence is monotonic. All right, here's another one. Again, get an idea just by looking at the first couple of terms, and then you can move on from there. So when n equals 1, I get 1 over 2 to the first minus 1, so that would be 1. When n equals 2, I get 4 over 2 to the second, which is 4 minus 1 is 3. So right now these just got bigger, okay? And then when n equals 3, I get 9 over 2 to the third, which is 8 minus 1, which would be 7. The problem there is that this next term is actually smaller. So I went bigger, and then I went smaller. Well, that right there disproves that this could be monotonic. So this is a sub 1, this is a sub 2, or let's say C. This is C sub 1, this is C sub 2, this is C sub 3. C sub 1 is less than or equal to C sub 2, but that's greater than or equal to C sub 3, so therefore it's not monotonic. And that's where this sort of monotonic, that's where writing the terms out can really be helpful. You can see right away it's not monotonic, or you can get an idea of what you think is happening for your inequality, and then you could go from there. And then we have the definition of bounded. And so a sequence, A sub n, is bounded above if there is a real number, capital M, such that A sub n is always less than or equal to capital M. So every single term of the sequence is less than or equal to this capital M for all n in the sequence. And that capital M is called the upper bound of the sequence. So if bounded above is one stop. We could also have a sequence that's bounded below. A sequence A sub n is bounded below if there's a real number, capital N, this shouldn't be an N, such that capital N is less than or equal to A sub n for all n. So every term of the sequence is greater than this single value, okay? Then the number n is called the lower bound. And then, get rid of this, a sequence, A sub n, is just considered to be bounded if it's both bounded above and bounded below. So there's bounded above, there's bounded below, and then there's bounded. And we get to the part that helps us with convergence of a sequence. If a sequence is both bounded and monotonic, then we could say it converges. So let's look at this bounded real quick. So let's say I have the sequence A sub n equals, say, 1 over 2 to the n. I could say that is bounded below by 0. Right? Why? I know that none of these terms are going to be negative. I also know that none of these terms are going to be 0, because the only way this whole fraction could ever equal 0 is if the numerator equals 0. I know that 2 to the n is always positive, so if I have 1 over a positive, I'm never going to get 0. So I know that every single term of the sequence is definitely bigger than 0. It's also bigger than any negative number. I could say it's bounded below by -2 or -7.8. All right, these are all things that, or this is bounded below this. We can talk about something called the least lower bound, or sorry, the greatest lower bound, which would be the biggest number that is still a lower bound. I think we're getting a little more complicated than needs to be here, but that's just the idea of sort of a lower bound. If I switch this sequence to negative 1 over 2 to the n, I could say it's bounded above by 0 for the same reason, just in the opposite direction. But in order to be just plain bounded, you have to be both bounded above and below. All right? And so you need that along with monotonicity to determine whether or not something converges. And so if we look at a couple of examples here, we could quickly come across some and see whether or not these are bounded and monotonic. So if we look at 1 over n, 1 over n is both bounded and monotonic, the idea being that it would be bounded above by 1 and bounded below by negative 1. And it's monotonic in that all the terms are decreasing, or I could even say it's bounded below by 0. Okay. One way you could see this is by graphing out the terms. So 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5. There's this upper bound, something bigger than 1, and we could just call it 2. There's this lower bound here, which I could say is 0. So it's bounded above and below. And it's monotonic in that all the terms are decreasing. So we have all that going on. So that therefore the theorem must converge. Okay, the series must converge. This one's divergent. It might be monotonic, and we could show that it is. In fact, we actually already did. No, sorry, we did not show that one was monotonic. But we could show that it's monotonic, but it's not bounded because it doesn't have an upper bound. The terms of this sequence are going to keep getting bigger and bigger, so there's no upper bound to it. And finally, divergent sequence, negative 1 to the n is bounded, but it's not monotonic. The terms just keep jumping between negative 1 and positive 1, so it's not going to be. So you need both criteria, both bounded and monotonic, to determine if a sequence converges or diverges in that case.